for 11.5 is getting things into a form that you can work with. Okay, so like for example, I put this in my notes here. This right here, let's just generally right now, if I said, how would you integrate this? What would jump out to you that you think you would try? Integration by parts is exactly what I would think too, right? Because integration by parts, you have a product rule here, doing reverse product, so maybe that's what we would do. It's not going to work because when we do integration by parts, we're trying to trim something down. Remember the x squared to 2x and the 2x to 2? We can't trim down a cosine or a sine. Do you see what I'm saying? So if I did integration by parts, you'd be doing it for a long, long, long time because you'd keep not getting things to go away. Okay? So what happens is that we need to go ahead and think about how can I manipulate this to get this almost like a substitution rule, which we want to make it. We want to get it, so how can I make this be in a position to demonstrate the chain rule? Like reverse chain, excuse me, substitution. Because sine and cosine, those are workable, right? So the next thing that you want to think about, well, is there any identities of cosine cubed and sine to the fourth? Not really. Okay? So the next thing you want to think about, this is where things get kind of like you have to, like I said, manipulate things a bit, is can I get a cosine squared or sine squared somehow? Anyhow, any way you think you can. I'm just going to do the easy one. Okay? I'm just going to go, we still have the side. I'm going to call this cosine x times cosine squared x. Why are cosine squareds helpful? Say that again. Cosine squared plus sine squared equals 1, right? Yeah. Cosine squared plus sine squared equals 1. That's based off Pythagorean theory if you didn't know that identity, right? Because if you have cosine squared plus sine squared, it equals the, let's go back just real quick. Remember, cosine's x, sine is your y. This squared plus this squared is 1 because the normal unit circle is a radius of 1. That's where that identity comes from. Okay? Anyways, at any rate, why this helps me is because I can write, when you have a sine squared or a cosine squared, you can switch to the other one. Like I can switch this to sine. So what I can write it as, and this is why it's helpful, I can write cosine x. Cosine squared is 1 minus sine squared. I'm here. So everybody, that identity is on your formula sheet. Okay? So under the trig identities, it's just you have to move over the sine squared. You're going to see why this is helpful now. Okay, this is helpful because now I'm going to distribute this. Okay, so that gives me a sine to the fourth x minus sine to the sixth x. It's kind of a bracket here. I'm going to leave the cos x here and dx. Anybody want to take a stab at why that's helpful now? Why did that improve our situation? So at the beginning I told you, yeah, integration by parts is not helpful with our trig ratio or with our trigonometry. So we want to think substitution. So let's just answer this general question. What would my u be here? I'm doing substitution. I've already given that away. We're going to do substitution. What would u be? Sine. What's du? So we now have things in a very workable situation. Because these, remember these are bracketed. So this is like, remember, don't forget, this is, so I'm going to have u to the fourth and u to the sixth. Does that make sense? So my substitution now will be this, what I just said, u to the fourth minus u to the sixth du. Now we're happy. Yes?
So why does the dx go with cosine, not
Because remember, it's when we're doing, this is with respect to u. So since, remember, the derivative of the x is dx. We've done that all the time for substitution. It's like x prime exactly.
Yeah, I get that, but you know how it, like, in the original, like, before you solved anything,
Mm-hmm.
it was, like, with the sine 4x?
It doesn't matter, dude. These are all multiplied. Everything's a product. So the order, like, yeah, I see I was here, and I just flipped it over here just so you could see it together. But it's multiplication, so it's interchangeable, right? Do you see what I'm saying? I didn't do anything different, Emma. I reordered it. So I pulled the cos x out of this one. Made that 1 minus sine squared x. Essentially, I just put the cos x right here after I distributed that in. Okay, so once I distribute this in, I had this times the cos x, and I put the dx there. So now, that's what we have. So we are going to integrate that, but before we integrate, we do need to go ahead and change our limits of integration, because remember, we use substitution. We don't use pi over 2 and 0 anymore. We have to do it from u. So all you have to do is, what is sine of 0? You guys should be screaming 0 at me right about now. Okay, sine of 0 is 0. And then what is sine of pi over 2? We all should be screaming 1 very loudly. Pi over 2 is at the top. Okay? Okay, so remember, sine's y. Sine of 0, you didn't go up at all. Sine of pi over 2, you're at 1. So my limits of integration changed from 0 to 1. I took these values from the beginning, and I put them in here to figure out my new limits of integration. Okay? So now, we are going to integrate. We're going to integrate u to the 4 minus u to the 6 du. Go ahead and get that down. I'm going to make a new page here so we can finish this off. Okay? So we have 0 to 1, u4 minus u6 du. We're going to integrate that, so it's going to be u5 over 5 minus u7 over 7 from 1 to 0. Questions on that? Well, sine was our u. U is what you're subbing in. So that's where we're going to get our limits changed from. It's from the u, not the du. That make sense? So if we subbed in for a cos, then we would put in a cos. We subbed in for sine. Okay? All right, so 1 to the 5th over 5, so 1/5. 1 to the 7th over 7 minus, you don't have to do this, I'm just showing you that this one's minus. It's 0. This is going to be 0 minus 0, which is pointless. So that's going to be your answer. 1/5 minus 1/7. Oh, wait, hold on. No, I'm right. Okay. Okay. Common denominator is the thing I just slipped. 7 times 7, 5 times 5. I'm going to get 7 over 35 minus 5 over 35 for your answer of 2 over 35. That is the answer. Remember, when you have limits of integration, you're going to get a numerical answer. It's not just do the integration and done. Okay? You're expecting a numerical answer. So again, yeah, it's confusing because you're going to have to play around with identities and try to form things in a way that makes them easy for you to integrate. Okay? So the biggest thing here is you want to try to get things in a form, like you kind of want to get a cos or a sine isolated so that you can maybe do substitution, because if you have multiple exponents, you're not going to be able to get those to cut down very quickly. So remember, always see about looking about cosine squared, sine squared, seeing what you can do in terms of your identities. Okay? That's the thing that's hard about this, is it's not direct. Okay? But we have 4 examples to kind of play with and keep looking at them. Okay? All right, let's check out this one. So this kind of says, in general, we can integrate a product of the form. This is just kind of showing you in terms of odd versus even exponents, what you want to play with. So like, for example, this being even is a problem because sine squared of x how would I integrate that? Because we don't have the cosine there. So this is a problem. So if you're saying, oh, okay, so Mr. Banger said do substitution. So this shows you why this won't work. So u is sine x. Okay, we just did this. So du is cos x. Don't write this down. Cos x dx. Well, what's the problem with that? We don't have a cos x, and you can't just do like, you know, before when we add a new number, if we're adding a 2, we make a 1/2. What would you do for cosine? Can't do 1 over cosine, okay? So no. We want to figure out, we see a sine squared. What can we do with the sine squared? So I'm going to go to another formula here. We are going to look at the double angle formula of cos of 2x. Cos of 2x is that. Why did I pick that? It's got a sine squared in it. So what I'm going to do is I'm going to solve for sine squared so that because this doesn't have any exponents on it. So I'm going to go -1. Okay. Divide by -2, which is going to give me so now we actually have something that I can use. Because that's easier for us to integrate. It doesn't have a square. Yeah. So we're just going to simply take this, and we're going to put this in here because it's easier for us to integrate. They are equivalent. We can't integrate the other one because we can't just add a cosine in there. Like I said, we can't make substitution because we don't have the piece we need. So when I integrate this one, the reason it's helpful is because you're saying, well, what's this one missing? Well, the 2, which will just be a 1/2. We can balance that easily. It's not a problem. Okay, yeah, Emma? What's that? We don't like the square because it forces us to do substitution. And when I set up substitution, my du is cos dx, and I have no cosines anywhere. And I can't just add those in. Does that make sense? Okay, and so then we've manipulated this to figure out a different form of sine squared x from our double angle formulas, which is on your formula sheet. It's this, and now we're going to integrate this because this is more friendly for us to integrate because it doesn't have a square. Okay, so this is what we're going to integrate. I'm also going to, did I pull out a -1/2 or just a 1/2? Just the 1/2, okay. So I'm just going to pull out the 1/2. Remember, we can pull out like coefficients to the front. So I'm just going to put it right here. And then I'm going to put, I'm going to write it 1 minus cos 2x dx. So all I did is I just reordered it a bit there. Okay, and I just took the 1/2 out. So I hope you see the point here. Do you see how much easier this is to integrate? What's the integration of 1? We should all be yelling x. Oh, these are the easy ones. You guys are scaring me today. Okay, x. What's the integration of negative cosine? Negative sine. But the 2x means that a 2 had to been, like if I took a derivative of this, I get a 2. So how do I balance a 2? A 1/2. And the other 1/2 is just out front here. And you have your, I'll do the plus c in a second. There is a plus c. Okay, and so all I'm going to do here to finish this off, guys and gals, is I'm going to distribute the 1/2 into here. 1/2 x minus 1/4 sine 2x plus c is your answer, because we don't have limits of integration. So that would be your integral. So question I got last time I remember teaching this lesson was somebody said, well, Last one, you made sine squared. You made it 1 minus cosine squared. 1 minus cosine squared doesn't help because it's the same issue. We'd be substituting cosine x. We don't have a sine x. So you could try that. Go for it. But it didn't work. That's OK. So this time I went to the double angles, and I found something that would not have a square in it that could help me integrate this easier. OK? All right. Any questions? Like I know, like this is not, like I said, it's not direct, so I get it. I understand you're just like, feel like just pulling it out of thin air. It's more of just you get used to it in terms of what you can use and what you can't. So in general, we can use integration of the idea that sine squared x is going to give you 1/2 times 1 minus cosine 2x, and cosine squared is going to give you 1/2 times 1 plus cosine 2x. So essentially, we just proved that. Okay. So just the idea that sine squared x is this is a formula it's given you. Okay, so another issue is that, so you guys see how they're saying that the functions that involve an expression in the form of something squared minus something squared can be integrated by making the trig substitution of x equals a sine theta. The reason being is because 1 minus sine squared theta and cosine squared theta, if I square rooted this, 1 squared is just 1, right? Sine squared theta and the square root of cosine squared would just be cosine. So it's the form that something squared minus something squared are the radical. We can take this pattern and use our identities to help identify it. Okay. So let me show you the actual piece here. So there, we're going to evaluate this in terms of just doing the integral. We can't do limits because there's no limits of integration. So it's kind of like substitution in the sense that we're going to let x be sine theta. So dx is cos d theta. They just went to thetas because they're already x's. Yeah. For like example 2. So that was because we said you have no cosine of x's that you could add in. So say what now? Yeah, this guy? Right? What would your u have been? You could make 2x your u if you'd like, but we know that the derivative of that's going to be 2, so we can just throw in the 1/2 with our, I don't want to say it's mental math, but just knowing what's going to happen. So it's not, cosine of 2x is not something squared or something that's in a bracket, so really we don't think substitution for that. That one's ready to integrate right away. Technically though, Janae, you could make u 2x, but it just would give you the 1/2. Does that make sense? Okay. Because when you take the derivative of 2x, it'd give you 2, and you'd be like, well, how do I balance a 2? And then you'd throw a 1/2 in. Okay, so we're going to let x equals sine theta for this substitution because we recognize this form, the 1 minus x squared. Okay, so we're trying to make it look like this. Okay, so if I just sub those things in, the sine thetas, I'm going to have 1 x squared, so that's sine squared, because we said x is sine, square root, the 1 stays a 1, minus sine squared theta, and then we said that dx is cosine theta, so that actually is on top here, time 1, d theta. So that's what we've changed it to with trig substitution. So this is back to what they're telling us. This helps us because Guys, this we can change to this. Because look, we have 1 minus sine squared theta in there. If I square root this, that's what we have right now, isn't it? So by definition, and that's what this whole thing's telling you, cosine theta is the same thing as 1 minus sine squared theta. And vice versa. Sine theta is the same thing as 1 minus cosine squared theta. If we had that, we could substitute. So this makes this, I don't want to be mean, but garbage. Go to cosine theta. Look what happens for us now. Sweet. And so now, I'll stop. Oh, I know I'm going fast. I'm sorry. Just want to get this out. That is the same thing as we're going to be integrating cosecant squared theta. Sorry. Trigonometry is kind of magical sometimes. So you went from that really ugly thing to the top to a simple, we're integrating cosecant squared theta. Okay, and the good news is that right there is on your formula sheet. Cosecant squared theta, if you integrate that, you get negative cotangent x plus c. Okay, we're not quite done. We're going to do one other thing with it. Okay. No? Okay.
How did you put the cos up there?
How do we put the cos up here?
First step, like you have 1 times.
Yeah, there? Yeah, because we said that dx is cosine theta d theta. So this right here was that, and I just slid the cos on top. See? Cosine theta d theta is dx.
Okay.
And so these are really together. I just slid the cosine on top so you guys would see this.
And how did you know that x was?
We identified x as a sign in just for substitution. Technically, technically we could have tried cosine.
Like, I just don't
Yeah,
get why you
cosine
have-
still would have worked. So, but
I just don't get why you have like an equation without any trig in it, and then you just make it.
right, it's because it's a specific situation, and that's what this is talking about. If you have something squared minus something squared, we can use a trig identity to help us with that.
Help solve.
Right. So like if this was a 3, we couldn't do what we just did. But if it's 25, we still can.
Okay.
It just changes, yeah. It's a specific situation. Okay, so what we're going to do for the second part here is that the problem is we did substitution. There's no limits of integration to change, but we did change something. We're not in trig land here. You're right. Okay? So while you're like, why can't you just substitute that? Well, we have to account for that, and that's what we're going to do now. So it's not going to take very long. Relax, relax. Come on, guys. It's Friday. It's Friday. You're doing calc. You're just enjoying life. Things are just tip-top shape. All right. So we have angle theta here, right? Because we changed to a theta. That's the angle we were just using, right? We know that essentially what is sine? So how about this? How about this? We know that cotangent theta, we just worked it out. We know that cotangent's that. That's the beginning. Yeah.
Is it negative cotangent?
What?
No.
All right, hold on. Okay. So we're thinking of things in the sense of, oh, sorry, that's my fault. This is the answer. My fault, my fault. I was like, wait a second. I jumped the gun a bit there. Okay. did I put this picture in here? I did put the picture in here. Sorry, the picture's already there. Let's do their picture. It's a little bit easier. Okay, so since it's an indefinite integral, we must return to the original variable. So we're returning it back to the way we were. So we have cotangent. So this is what the original is. Okay, so the original is sine. Why is sine? So what is sine? Just think about it. What is sine? Just let's go back to math 10, trig ratios. Opposite of hypotenuse. What's opposite of hypotenuse here? X. X over 1, correct? We made sine theta x over 1. Okay, I apologize. What's that? How do we get cosine? Pythagorean theorem. Pythagorean theorem gets us this side. This squared minus this squared, right? 1. Okay. Sorry, that's a piece I just threw the answer before that. That's very confusing. I apologize. So now our answer, you guys said we know it's negative cotangent theta. This is theta. So we know that cotangent is adjacent over opposite because it's flipped tangent. So it's going to be this over that. Yes. We made a triangle to get the values of opposite and adjacent. So, no, good question. Okay, so if good question, guys, stay with me. This is great. Stop taking cell phone breaks, ladies. Jeez. How do I know that what? Okay, so the hypotenuse is 1 because we set that. We said, hey, our sine is x. So our sine is x over 1. So we set that. That's how we're changing it. Yeah, and so then the only mystery is, well, where did this come from? From Pythagorean theorem. The point in doing that is because at the end of the day, we still said, I don't want to say out of the blue, but we still said we're going to make our x be sine so we could handle, because we like this relationship with trig. And so we changed this. Since we changed it, we had to say, okay, well, what'd that do to us? That gives us this relationship for my cotangent, so I can write my cotangent back to the original. Because remember, our question was x squareds. So we don't want to give an answer of cotangent because that's not making sense. What is cotangent? Cotangent is that, based on what we changed. Okay, here, I'll pause the video. We can freeze for a second. It's no problem. Example here. Okay. All right. So we're going to look at an ellipse. Okay, we're actually going to find the area of something. So that's good. We're going to find the area of that ellipse. An ellipse is a not perfectly, an oval. Not a perfect square. Well, I think an ellipse is symmetric. Yeah. Yeah, it is symmetrical though, so it's not an oval. Ovals aren't symmetrical. Okay, so we are going to want to integrate this still. Okay, we're still going to want to do some of our math skills here, but what are we going to do first? What's wrong with this right now? What don't you like right now? Yeah, get y by itself. Yeah, let's solve for y. That's the first step. So let's do that first, okay? We're going to get it in terms of something. Times it by 4 now, it's fine. The book put these together first. It doesn't matter, okay? So they just made this 25 over 25. Just real quick. And now you'll times it by 4. It doesn't matter, Jeanette, you can. I actually, in my notes, I didn't, but the book did this way, so I was just going with what some of you guys are looking at. So, so it would be 25 minus x squared over 25, and the whole thing times 4. And then what we're going to do is we're going to pull the 4 over 25 out as a fraction. And we're going to square root. We do that because look at that. We like those, right? Yes, we do. Stop it. Negativity. Where's the what?
I was like busy drawing the circles, so I didn't see you doing all that.
We solve for y.
Okay.
So I minus the x squared 25 over. I got these to be a common denominator. Put those together, times the 4 over, pulled 4 over 25 out, square rooted both sides. We're just solving for y.
Wait, why? Why could you square root both sides instead of doing one? Okay, because they're
Yeah, they're multiplied exactly. Okay, so this ends up being, so we have y now. Y is plus or minus 2 over 5 square root 25 minus x squared. So we're trying to find, bless you, we're trying to find the area of this. So what we want to do is we need to use that, for example, which of these cuts is bigger? They're all the same. Okay. Second question. And now I know you're not thinking we can't answer that. Yeah, they're all the same. It's symmetrical. Okay. Next question is what are the zeros? The x-intercepts. 5, right? And do you guys see that comes from 5 squared 0? Negative 5 squared 0? Okay. That's going to be what we're going to do our limits of integration from 0 to 5. We're going to find this slice and do what with it? Times it by 4. Correct. So we're doing 0 to 5 because that's how big our ellipse goes till. So what we're doing is we're staying in positive land. We want to be in quadrant 1 because quadrant 1 is all positive numbers. And we're going to take that value and times it by 3 instead of worrying about negative issues. So that's why if you're saying, why'd you cut that slice? Because this slice is positive, positive. It's a much easier slice to figure out. And times it by 4. Because there's 4 slices? Okay. Okay, so are we good? I feel like we're going to have to do this again on Monday. All right, so we are going to integrate. So since we're dealing with positive, we don't need the negative piece because the negative piece would actually be the bottom here. So we just need plus 2/5. Okay, so we're going to do, I'm over here now. We're going to do, just making sure we know where I'm at. And you can times it by 4 now or at the end. It doesn't matter. So like the book times it by 4 right now and makes this 8/5. Okay, do you guys want to do it now or later? All right, now.
Why is it not like a plus or minus instead of 2/5?
Because the plus and the minus means the top and the bottom. Because it kind of, if like a parabola, it flips it. So we're just saying we want the plus. Does that make sense? Okay. Stop it. Okay, so times this by 4 now. 8 over 5. Whoa, what am I doing, radical land? Okay. I said you could do it any time. Yeah, it's okay. This is good for the video. It's okay. Yeah, the 4 is a constant, so I can do it at the end, or I can do it out front now. It's not. It's going to get us where we want to go. We will after we integrate. We're going to integrate now. So listen, this is good. This is good. So we're going to integrate We're going to use trig substitution. That's the lesson. So that's what this is here for. But we're going to get a value here that's going to represent the area of this shaded piece. And then we times the 4, and the 8/5 is going to multiply to give us the whole ellipsis area. So we're going to integrate. This is going to give us this piece with the times the 2/5. Okay? And then we times that all by 4, which has already been put in. Okay? That's all right. So the 25 minus x squared should be familiar from what we just did. So what would you make your x? Sine. Stay with the sign, yeah. Okay, let's go and get a new page here. All right, so we are at 8/5, 5 to 0, square root 1 minus, no, 25. I'm just rewriting it, guys. X, we're going to make sine again. Scratch that. We can't make it sine. It's got to be, why can't I make it sine? What's that? I have to make it 5 sine because of the 25. What's that? This is why, okay, this is why this is a good point, because when I plug this in, I'm going to square it. What's that give me? 25. They both have a 25. I pull a 25 out. What's that give me? 1 minus sine squared. What do I love about 1 minus sine squared? It's cosine squared. Can I square root 25? Can I square root cosine squared? Yes. Bingo, bango, bongo. Yeah. So the reason is we're trying to get the 25s to match up. Oh, sorry. It's not an x. We said theta. Just a second. This is a 5. Okay, so the part we missed, well, not missed, but we just weren't got to yet. Remember, if we made x, we have to know what dx is. So the derivative of this would be 5 cosine theta d theta. That's just normal. It's not a problem. So that goes where the dx was. So that's right there. This is a 5 cosine theta d theta. The sine squared has a square on it because x squared. So we squared the sine, squared the 5. 25 sine squared theta. Everybody good? Okay, so now, like I said, we're going to pull the 25 out of here because we get that. We like that because now we have that. We like that because that is yep. Okay, question? They're a product. Radicals multiply together. What? It's a product. It's not a plus sign anymore. That's why we're really happy, is because we changed this binomial to a monomial, which makes this one product. So you can square root now. That's actually the reason we did it. Yeah, we can try that later if you want. Yep. Yeah.
Under like the one where it's like square root 25 times 1 minus 9. Yeah, that one is the 5 cos.
So this is all coming down with us.
Okay.
Yep. Okay. Is everybody good? So then what we have now is we have 25. 25. It's going to come out. So we're going to times the 25 here. I'm just going to take the constant all the way out. That's 40 now. So guys, just stay with me. This is 25. I multiplied it to that. 25 times 8 over 5 is 40. And I'll stop right here. We still haven't integrated yet, PS. Get that down. I'll pause the video for a second. If you want to ask questions for here, we do that. So 0 and 5 was for this. It wasn't for this. Okay, so what we're going to do is you need to understand how, so essentially, how would this be a 0? What would theta have to be? 0. Good. So that's the easy one. How would this be 5? Good, but we don't put 1, we put pi over 2. That's your new limits of integration. Okay? Because again, we changed, right? We went from this to this. So I've changed my 5, 0 to the new limits of integration within sine. So watch. If I put 0 in, sine of 0 is 0. That's 0. Match. If I put pi over 2 in, sine of pi over 2 is 1 times 5 is 5. Match. So we now have changed our limits of integration so that we're not really messing things up. Okay, so this is what we'll integrate. That didn't really change. Integration is going to be the same. Did anybody see anything or research what they're going to do next with the cosine squared? What did you find? Yeah, the one I have, I use the 1/2. Yep. So we want to use the one with the cosine squared in it, which would be, we actually want to use the cosine 2x one. Okay. So this is the one we're going to use, and I'll use it on the next page. We have like 3 minutes left. Just power through here. I know you're exhausted. We're going to use this one. That's the one we're going to use. It's on your formula sheet. And when you solve for cosine squared x, you're going to get 1/2 cos. You're going to get that when you solve for cosine squared x. So that's a double angle formula that we are changing into getting cosine squared by itself. Okay, so hold on. I'll start over in terms of, not all the way over. I'm going to start from the top of how that comes about. Just hold on. Cosine 2x is, in your formula sheet, is 2 cosine squared x and then minus 1. We're going to solve for cosine squared x because that's what we're going to replace our cosine squared theta with. Theta x is irrelevant here. Okay, so first thing, add 1. Second thing, divide 2, which we're just going to call that a 1/2 out in front. So now we know we can replace this with that, which we do not have the chain rule situation. Yes? Why do we like the cosquareds?
Why do we want to change
Oh, because we have that chain rule issue again. If you make this u substitution, u is cosine x, your du is negative sine x, we don't have a sine anywhere again. This is coming off of, so this is combining example 3 and 2 into one longer problem. Okay, so this, guys, is what we're going to integrate. We still have the 40, right? Yeah, we have the 40. We have 0 to pi over 2. We have a 1/2 that I can hit to the 40. Is that okay? So I'm going to call it 20. Okay, let's integrate this thing finally. You with me, Zach? Sorry, we were actually in theta, right? It's your fault. All right, so here's what we're going to have. Integrate that. That's going to be integration of cosine is what? Sine? Yep. We're using theta. This was just me solving the formula in your formula sheet, which we're in theta for our problem, so we're back to theta. Okay? Okay, 1 becomes just theta, and we're looking at it from pi over 2 to 0. and we have the 20 out here. Are we ready? We just plug in now. Pi over 2. What's 2 times pi over 2? Pi. Yep. 2 times a half is a whole. Yep. Okay, so that's 0. Because the 1, right? Okay, so we're good. That's 0. That's just pi over 2. That's by himself. So 0 plus pi over 2 times 20. What's that? Okay, now we're going to minus the second piece, which is pointless because 0, 0. Your answer is 10 pi. 10 pi is the area of that ellipse. 31.4-ish. Enjoy life.